Yeah, so I was firing these rocks with lasers. You're listening to The Cosmic Cast.
Hello everyone, and welcome back to another episode of The Cosmic Cast. You're here with me, lead bassist from the death metal reggae band Sunshine Dying Times, Rick Biver here. To my left, we have the harpist from the Manchester-founded acid jazz orchestra, the Bradford Funkadelics, Tom Harvey.
Hello there.
And you'll know the final speaker from his many hit singles, such as You're Barking Up the Wrong Sycamore and Hey, You, Open Up Your Nose Holes and Smell These Fingers, Dr. John Burnett Fisher.
Hello there, and congratulations, Ricky. That was our 5th attempt at doing this intro.
Oh, I'm crying.
Welcome to another episode of the Cosmic Cast. Thank you all very much for tuning in for another week. So this week it's just the three of us, no special guests. We're just going to have a brief chat about what we've been up to recently and some exciting news. I've also had a paper published very recently, so
Congratulations.
Thank you very much. Have a bit of a chat about that. And we're in a very giggly mood this afternoon, I think it'd be fair to say.
So I officially have just under 2 months left before I finish my PhD.
Wow.
Which is, I feel like, you know, when you're drowning, and you say you get that just sense of relaxation just before death takes you away. I feel like I'm at that stage now. Like, I feel like I'm doing everything I can, and I don't worry about what happens afterwards, because there is no afterwards. It just ends.
And are you finding people are just coming up to you and saying, how's the writing up going?
Actually, no one has asked me that.
That's good.
Yeah, no one has asked me that, which is good.
How's the writing up going?
It's going great. Yeah, it's going really good. Thanks, Tom.
Oh, that's convincing.
Yeah. No, it's going fine. I think everything's going fine. Should have a paper submitted within the next week or so. So everything's going okay. I can't complain. And I've got 4 papers essentially written up. They won't be in the phase where they're ready to be published, but they're high enough quality to be a dissertation level. So feeling okay about it. I'm more worried about jobs, because I think if you guys had listened to the first episode, that was back when I was first applying for jobs and still nothing as of yet.
Well, that was only a few months ago, though.
Yeah. But it gets to that stage where you're looking at these jobs and the availability of them starts to dwindle. And even those that are available won't start until after you've already finished your PhD.
Yeah. I mean, it can be disheartening. All
of my jobs actually are abroad that I've applied for. So one's in Madrid, one's in Munster, one's for NASA in America.
The NASA postdoc
PDS
program.
Yeah. So yeah, just see what happens essentially. But
and where would you want to go out of that bunch?
Honestly, I've got to that stage now where originally I really wanted the NASA one, but now anything will do.
Yeah. Well, I think it's quite similar. I mean, that's pretty much the position I was in when I was applying for jobs after my PhD. I started off wanting things that were fairly local in the UK, and by the end I was like, yep, anything will do.
Yeah, but I really try not to base my career trajectory on yours.
Well, yes, perhaps you'd be wise to do that.
But no, I would be happy with anything. I've only applied to jobs that I really want, I guess, which is quite selfish of me. But
well, I mean, you got to do what interests. There's no point doing a postdoc that you hate, because that would be a miserable experience.
And how is your first year going?
It's going well. I suppose I'm sort of at the opposite end of the...
Are you 6 months in now?
Yeah, just about. Yeah. I'm kind of at the opposite end of the writing spectrum in that I've kind of started properly working on my transfer report. And for anyone that hasn't done a PhD, that's basically the summary of the work that you've done up to now. And in this case, it's largely taking the form of literature review, which kind of helps the department decide whether or not you're going to be able to transfer into your second year of your PhD. And it's going well, I think. Obviously, there's a lot of theory to get to grips with regarding... It's quite a diverse range of subjects between different types of meteorites, asteroids, and also looking at lunar material as well. But it's kind of been interesting in that sense from a comparative point of view, because it's reading two quite, well, relatively similar bodies of literature, but noticing that there are differences between the two as well. And that's due at the end of June, so there's still quite a while to go, and I've done quite a lot of writing, but it's about making sure that it's succinct and actually getting across the point that I want it to.
Yeah. So essentially what Tom is handing in is what we call a literature review, and it's what it is you're reviewing literature to see where there are parts missing and what research needs to be done. But part of the irony is when you start a PhD and you're in your first year, you don't really know the trajectory of your project yet. So to say, oh, this is where the gap is in the market of science that I need to be filling is a difficult question to answer. But I guess at least it lets you get all the background knowledge you need as well.
Yeah, definitely. And it's meant that I've been able to sort of refine what exactly I want to look at a little bit as I go. Starting with a more kind of general, just thinking about metals in impactites and impact materials, and now looking more specifically at like a specific group of meteorites and kind of lunar impact rocks as well. So yeah, it's going well though, I think.
Are you enjoying writing though?
I don't particularly enjoy the process of writing, but I also don't not enjoy it. It's very much obviously a necessity. It's part of the job of doing any research. I suppose something that makes it a little bit difficult is having to constantly be reading and writing at the same time.
Yeah, I don't think coming into a PhD initially I was quite prepared for quite how much writing is involved in being a scientist, I guess.
Because I guess the only other big projects you will have done where you have to write a lot are your dissertations through.
Yeah. But also you look at papers and you think, well, they're about 10 pages long. How hard can that be to bash out? But it turns out writing at academic level is actually very difficult.
Well, for some, John, it's a difficulty.
Okay,
for some people, they struggle. For others, such as, myself.
Right.
It's like lying in a lilo down one of those lazy rivers. That's what it's like for me.
Incredibly traumatic because you can't swim.
Yeah, I got stuck in one of those.
I think one of the most interesting pieces of advice that I've been given is just to write about everything that I do. So it's not just writing about the literature, and it's not just writing about results or analysis, but also trying to record the methods, the details of the data collection that I wouldn't have necessarily expected to need later down the line. But I am assured that it will come in handy. And I think having something to always write, even if it's not what you're working on at that point, is good because it keeps you writing and it keeps you in the habit of it.
Yeah, you'll find throughout your PhD, you will write a lot of stuff you never use.
Oh, yeah.
Yeah. So Tom was asking me yesterday, is there any data you've got through your PhD that you aren't using for your dissertation? And I know, especially in GIS projects such as my own, where you're looking at satellite images, and you're taking readings of different things from these images, you will get a bucket load, and that's the scientific terminology, a bucket load.
A metric bucket load.
A metric bucket load of data that you don't use because with papers, there is a narrative that needs to be filled. And so you will write a lot of stuff that doesn't fit the narrative, and you will take a lot of data that doesn't fit the narrative. So there's a lot of stuff you won't end up using, but you're right, you should just keep on writing regardless of it, because one day that stuff might be useful for something. So.
Yeah.
And something else that I've really taken on board for those listeners who didn't listen to the Jamie Gilmore episode is this ability to just find interest in anything scientific. And I've taken that, and now I find reading papers that aren't necessarily to do with Martian fluvial systems, such as just looking at papers about, John's paper that we'll get onto. You read it with this different outlook of, oh, actually, this is really interesting. Whereas before, it's very easy, I think, in a PhD, especially, to get very narrow-minded about just looking for stuff that hits the brief of what you're researching.
I wonder if part of that is the the extent of the detail that you're trying to get out of it. Because if I'm reading something because I want to get everything out of it, then I find that's often quite hard because the process of trying to ensure that you haven't missed something, that you've understood the message right, and then thinking about how that links in with what you already know about the subject is quite different to reading about a paper which is maybe kind of adjacent to or significantly outside what you're kind of researching in detail, where you can sort of enjoy the novelty of the method and the conclusions without having to extract as much meaning from it.
Yes, I think there is this element of when you are reading papers, you feel like you need to get something specific out of it. It's almost as though if you were watching television and every program you watched, you wanted something that was relevant to what you're doing in life to get out of it, rather than just reading it for the enjoyment as well.
Yeah, that's a good way of putting it. I mean, specifically, I was looking at how much energy is released in an impact of a certain size with a certain type of impactor. And I looked in loads of papers to try and find that information. And in the end, I was just frustrated reading because I couldn't find exactly what I was looking for, despite looking in what I thought would be the right place. And that, if anything, made the reading just harder and harder, because the more frustrated I was that I couldn't find what I wanted. Whereas if you're just reading something, and all you want to do is enjoy reading about the science of it, but with enough of the context background that you can read it at that level, then that's a lot more fun. That's for sure.
Yeah, I mean, the same thing can be said with conferences as well, I suppose. It's very easy just to go to sessions that are directly relevant to whatever you're studying, and you miss out on cool, other interesting areas that you might miss otherwise. But I guess, it's a balance between sort of time management as well, I suppose, where you've got only a limited amount of time in the day and you need to...
I think something that we're very lucky with is that our jobs are something we really enjoy doing. Yeah. So you almost get to the point sometimes where you forget, oh wait, this is my job that I'm doing. I'm not doing this for just enjoyment. I'm doing this because it's work. So you're right. You have to balance reading these papers with writing your own papers, so getting the relevant stuff really for
getting
them.
on with it. Yeah, and I find that particularly at a postdoc level, there's always a pressure to be churning out papers, and you can get certainly very easily sucked down into a vortex of, well, is this directly relevant to me advancing a paper? No, therefore get back to it.
Yeah. So is there actually? So you don't need to be specific for the role you've got here, but in general, are there advertisements where they say, hey, come to this postdoc, but we expect this many papers out of you?
No, they won't say that. It'll all be sort of unwritten expectations of what an academic in a certain field can reasonably achieve in a given period of time. And some bosses will be better than others in terms of corralling postdocs into writing papers. But I mean, in a way, it's not about someone looking over your shoulder saying, keep writing. I mean, you do it as well because you know that that's what it's going to get you a permanent job, and so it's almost a pressure that you put on yourself to say, well, I need to keep writing, I need to keep publishing to compete and to stay above the rest. Yeah, it can be challenging, and it's very easy to get sucked down, as I said, into a vortex of worrying about publication records.
But so I only have one publication at the moment, well, real publication. I have abstract publications from LPSC and things like that. And I'm only a second author on the publication I actually have. So I didn't really have this amazing feeling of, wow, I've got something published. But what is the feeling like when you've done this work and it finally gets published? Because for people who don't know, there's a lot of hoops. It's not just you write a paper, you send it off and someone publishes it.
Yeah, the whole peer review process can take ages.
So that's when people actually read your paper you've sent in.
Yeah, and they pull it apart sentence by sentence, and they give you feedback, and then an editor will then forward that on to you, and you make your rebuttal and any changes, or you can write a statement saying why you disagree with what the reviewer said, and then the editor will make a decision then as to whether it needs to go back out to review, whether they can accept it at that point. And certainly my experience has been most papers have gone back out to review because editors like to be thorough, I guess. They don't want to publish nonsense in journals, I suppose.
Which is good.
Which is good. It's how science should work. But no, it's a long, drawn-out process. And I think the feeling of when you actually get that email through saying it's been accepted for publication is more relief than anything else.
So it's no great overwhelming feeling of success, just a relief, just a sigh of relief.
Yeah, well, quite often this process can take months, and so by that point you're already well into your next paper, and on your energies and your thoughts are on
something else.
Something else?
Yeah, fair enough. Yeah. So on that subject, you actually have a paper published, though.
I do, yes, and this is a paper which I'm quite pleased with. Yeah.
So when did you start work on this paper, and when did it get published?
Well, so I suppose this paper. So I guess there are different types of papers. There are quick and easy papers that you can write, and so an example might be just doing a meteorite classification paper. That's something that you can just collect a bit of data and just get out there relatively rapidly. Whereas,
for those who don't know, what is the downside to just doing something like that?
Well, it's not as high impact, so it's not as citable, and it's just.
So it's like making a video and it not getting very many views.
Yeah. Well, it's just like filler, I suppose, in a way.
I guess it's probably worth mentioning that the success of an academic paper is often measured in terms of its kind of impact.
Yeah. So this is a really good point, actually. So people often talk about individuals' H index, and so someone who has a high H index will be regarded as having quite a publication output that's been highly cited. And so the way it works is that to have an H index of 1 means you have one paper with 1 citation, and then 2 would be 2 papers with 2 citations, and it keeps racking up like that. So
essentially, it's not just about getting loads of papers published; it's about
getting
that
them
paper
cited.
Yeah. So people referencing your paper in their papers.
Exactly. Although interestingly, it doesn't discriminate as to whether the people citing you are saying it's complete rubbish.
Yeah, exactly. So someone could reference your paper saying, "This is wrong."
Yeah.
But
well,
you still get
that's still
counted.
important, though, isn't it? Because if you're talking about its impact on scientific knowledge, then the debate as to whether or not you've progressed, you know, is as important if it's that's not it, as if it's yes, that is it.
Yeah. Well, yeah. And also, I suppose, you know, as geochemists, you hope that the data is still correct, whereas your interpretations might be absolute garbage.
So on that note,
speaking of absolute garbage interpretations,
anyway.
So what's your paper about?
This is a slightly bigger body of work, and coming to that as well through what Ricky was saying as well. This pretty much represents, I guess, one of the major outputs from the last funding cycle at Manchester. So this was the main project that I was employed to do, and this represents some of the bigger conclusions of that project. And the paper is about understanding how the lunar crust formed. So it's really important to understand how the lunar crust formed, because it's what's known as a primary crust, and so it's one of the first crusts to have formed on the moon. And it's really old. It's sort of 4.3 or even older billion years old. And so it's a way of looking at what the early development of rocky bodies like the Earth or Mars might have been like, because obviously no rocks of that age are available to us on Earth, and even less so on Mars. They're accessible for us to study. So if we want to learn about how planets sort of first form and develop, looking at the moon is an excellent opportunity to sort of...
Especially because the moon is thought to have been derived from Earth material.
Well, yes and no. That's less sort of relevant, I suppose. It's more about what are the kind of mechanisms that generate crustal formation. And so
obviously on Earth we can't look at that because, as you said, we don't have any surface rocks that old, because all of it gets recycled.
Yeah, so because of plate tectonics and all that, there's nothing particularly that old on the Earth. I mean, you do get some stuff that are a few billions of years old, but they tend to be quite rare. When you look at most of the ocean sea floor, for instance, you know, that's well less than a billion years old. I can't remember what the oldest sea floor is. I think it might be something. It's a few hundred million years old anyway, I think. The reason why we think we can apply this lunar model of crustal formation to the other planets is because all the planets, all the rocky bodies, so that the planets and things like the moon, are thought to have started as a giant ball of magma. And so it's about understanding how that giant ball of magma crystallizes and differentiates into a core or a crust and all that kind of thing. And so if you can understand that on the moon, it gives you some indication of what might have occurred on Earth. And so in the case of the moon, you have this thing called the lunar magma ocean hypothesis. And this states that, as I said, it's a ball of magma, and you get your heavy minerals like olivines and pyroxenes will crystallize first. Because they're dense relative to their surrounding magma, will sink, forming the lunar mantle. And then at some point, we think at about 70 to 80% crystallization, plagioclase will start to crystallize. That will then float to the surface because it's less dense than its surrounding crystallizing magma, and that accumulates to form a crust. And we term this rock an anorthosite. This is because the plagioclase, the variety of plagioclase that's crystallizing is very calcium rich. It's known as as anorthite, and so a rock composed of just anorthite is called an anorthosite. So this was a model actually that was first proposed just after Apollo 11 brought back its samples. So it's a 50-year-old hypothesis. And by and large, that sort of general tenet of a magma ocean crystallizing like I described is generally held true. But what's quite interesting is that as analytical techniques have improved, we can measure chemistries of rocks better and better as the decades go on. And that's led to sort of refinements and quite tweaks to this model. And people have argued, I suppose, over the sort of the fine details of quite what goes on during this sort of sinking of crystals and flotation of crystals. And so this is what this study was aiming to address was, does the chemistry of the rocks explain this sort of crystallization flotation model? Is it consistent with that? Or are some of the variations that have been proposed in the literature over the years actually a better fit? So we focused on trace elements within these anorthosites. And
so what are trace elements?
So yeah, trace elements, these are elements that are present in the mineral at abundances under 1,000 ppm. Okay. So in the case of plagioclase, the mineral structure of plagioclase is made up of elements such as silica, calcium, aluminium, that kind of thing. Whereas trace elements will be things like rare earth elements, will be things like some of your transitional metals, and they'll only really be available or they'll be incorporated into plagioclase at only a few to tens to hundreds of parts per million. So quite small abundances. But the important thing about them, though, is that when you ratio them, and I think this is kind of what Emma was talking about the other week, is that when you ratio them, they don't change as a function of crystallization. So you can imagine a magma crystallizing plagioclase. The plagioclase wants to take in the things like calcium and silica and all that kind of stuff. And so the concentration in the melt will decrease in those elements. But the trace elements, they don't really like to go in the plagioclase crystal structure. And so
they'll
remain in the melt. But importantly, their relative abundances will also stay the same as well. Yeah. And so, as I said, when you ratio them, that ratio shouldn't change as crystallization proceeds. And so if you take this classical model that was first put forward in the 70s of just simple crystallization of plagioclase that then floats to accumulate the crust, you shouldn't really see a change in the trace element systematics of these rocks. They should be more or less constant over a whole suite of rocks as crystallization proceeds. But that's not actually what we observed in some of these rocks. So we were analysing Apollo 16 anorthosites. Apollo 16 was the mission that sampled some of these anorthosites up in the highlands. Most of the other Apollo missions were down in the lowland Murray basalt areas.
So why did they specifically need to go to highlands for you to be able to do this?
Well, that's because the Murray basalts don't have any of these anorthosites nearby, and so it was...
it's a lot younger material.
Yeah, the Murray basalts are younger. They were initially, the Apollo missions wanted to land in these Murray basalt areas because they were quite flat and quite easy to land in, whereas these highland areas are a bit more undulating. There are a lot more boulders and fragmented crap, for want of a better word. And so it was certainly a lot more challenging to land in some of these highland areas. But anyway, so Apollo 16 obviously was successful. It returned a lot of these anorthosites. Now, some, of course, had been analysed for their trace element chemistry before. A bunch of them, interestingly, had never been analysed for their trace element chemistry. So it was the first time that we analysed some of these rocks, which was quite exciting. But anyway, it was a comprehensive suite of about 11 samples in total, I think. And what we found was that the trace element ratios were varying in this suite. And so this is inconsistent of this simplistic picture of plagioclase flotation.
Yeah.
So the bottom line of what we are proposing is something called mantle overturn. What this states is that rather than this simple plagioclase flotation, one thing that people didn't consider was the crystallization of a mineral called ilmenite. Ilmenite is a titanium-rich mineral. It's really dense and so will sink as opposed to float and will contribute to the lunar mantle at that point. Modelling suggests that ilmenite probably started to crystallize after about 95% solidification of the lunar magma ocean.
Okay,
so it's
very
quite late stage, yeah. But the important thing, though, about the ilmenite is because it's so dense, when you start to get clumps of it forming in the mantle, you might start to get mantle overturn. And this is where this really dense stuff, which is sat at the top of the mantle, will through gravity sink.
Okay.
And as a result, that will sort of start some vague sort of convection motions going in the mantle.
Because it's moving that material.
Exactly, yeah. And so so stuff's going down your ilmenite-rich material and dragging all sorts of other bits downwards, whereas you're getting these really hot stuff, or hot mafic minerals from the bottom of the mantle up. And that can cause decompression melting. That then has the opportunity to then mix with the overlying magma ocean that's crystallizing your plagioclase. And the thing about decompression melting is that they're likely to be quite small degree partial melts. In terms of explaining what partial melting is, this is the general concept of how we think rocks melt in the mantle to produce lavas and ultimately volcanoes, I guess. And when you produce melt in the mantle, you're not completely melting everything. Everything is not completely molten down there. It starts off as a solid, and as you increase the temperature, you'll start to get small blebs of melt form from the minerals that are in the mantle. And obviously, the more melting that goes on, the more melt will be generated that's able to percolate up, and that will eventually lead to magmatism. And so when you have very small degrees of melting, due to the way this melting process in the mantle works, it tends to be really enriched in all the incompatible elements. So it's kind of like crystallization in reverse, I suppose, because all the main elements that form up the minerals, they want to stay solid because they're nicely bound into minerals. Whereas all the elements, like the rare earths and the transition elements that don't really want to fit into those crystal structures very well, they'll much rather go into that melt.
Because they're easily lost.
Because they're easily lost, exactly. Yeah. So when you have very small amounts of heating and you have very small degree partial melts, they'll be very enriched in all the elements that are not part of the rock forming mineral. And then the more melting proceeds, the more that you basically get wholesale melting of various minerals in the mantle, and you'll basically get all the other elements in the melt that will then percolate up to form the volcanism.
And that's how you're getting these trace elements.
Exactly, yeah. So this decompression melting is going to be small degree partial melts. That's going to be very enriched incompatible elements. So it's a mechanism of producing variable trace element abundances, or introducing variable trace element abundances into the magma ocean that's then crystallizing plagioclase that can then accumulate.
And that's why you're getting these different ratios then.
Exactly, yeah. So I mean, you can sort of say that, well, maybe it's sort of a geographical thing where some parts of the moon you're melting more, and therefore you could have a spectrum of sort of different compositions being introduced into the overlying magma, I suppose.
So is that still a primary crust process, or is this happening after that's kind of largely formed?
Yeah, so that's a good question, and I think that's still sort of open for debate. I think it's still
not... You said at 95% crystallization that this should start to occur.
Yeah.
So yeah, is that still primary?
Yeah, it blurs the line. So these so-called canonical models of the moon would state that you'd have this crust building episode, and then a bit later on you'd have these intrusions of basaltic material to make these plutons. These are the so-called secondary lithology. So these are things that they're known as the Mg suite and the high alkali suite, but they're basically just gabbroic intrusions in the crust. And canonical models would state that this happened a bit later on. But I think with what we're seeing in the anorthosites, that sort of line is a bit blurred, and that really there's no clear sort of transition between going from what is very clearly a primary crust building episode into more secondary processes. And as you say, particularly when you're starting to consider things that are going on about 95% solidification, obviously you're starting towards the end of magma ocean solidification, and you're bound to get all sorts of complications. And I think it's quite interesting too, because it means that most of the anorthosites that we have, sample late stage crust building. We don't really seem to have many anorthosites that sample these initial accumulations of crust building, presumably because well, actually it's weird, isn't it? I guess it must be impact that's mixing all this material up, because you'd imagine that if you can think about the sort of stratigraphy of the crust, you'd imagine that the younger stuff would be at the top and all the older stuff is being accumulated at the bottom. So it's obviously being mixed up somehow, probably through impact, but Yeah, that's a good
impact
point.
of other things onto the moon.
Yeah, exactly. Yeah. So I guess the problem is that a lot of these northosites that were sampled are not direct bedrock. They're not actual outcrops that were hammered. They're mostly just very large boulders on the surface. And I guess it's one of the big problems about lunar geology in general, specifically for the highland lithologies anyway, is that we're using big boulders rather than outcrop, and as a geologist, that's like a cardinal sin is to sample a boulder rather than actual outcrop. So
what sorts of analyses were you doing on them? Because I know like scanning electron microscopes, microprobes aren't necessarily enough for getting the sort of concentrations of trace elements that you're talking about. What were you doing?
Yeah, so I was firing these rocks with lasers. So this is a method called laser ablation, ICP-MS. And so what you do is that you fire a laser at a sample, a very small spot size. So I think the spot size I was using was about 60 microns. And that actually ablates the material into a plasma, and that plasma can then get carried away and analysed by a little quadrupole mass spectrometer. You're physically removing material and analysing it rather than some of the electron microscopy you might do, which is...
You got to destroy parts of the Apollo samples then.
Yes, very small parts anyway.
Very small parts.
So you've got to get permission to do that, of course. Yes, and I did a bit of SIMS work as well, which I think Roma again mentioned a few months ago, didn't he? So again, this is directly ablating material and analysing it. But laser ablation, it's quite good really. Like it's quite rapid and you can get a lot of results very fast. I'm a big fan of laser ablation.
So if we're at 95% crystallization, how long do we think this process was going on for then?
Yeah, it's a good question. I mean, part of it comes down to how long does overturn take to occur. And it's been modelled numerically by a few groups in America, and it sort of suggests that these processes can occur over timescales of millions of years. But the crustal building episode itself, just based on some of the radiometric dating that people have done on some of these samples, are thought to have lasted only a few 100 billion years. So quite rapid in the grand scheme of things, I suppose. But yeah, in terms of precisely what the timescales are, is certainly an open question, and is actually really important in figuring out the general chronology of crust building, because part of the reason why people have started to question some of these canonical models is because we used to have two distinct sets of ages. All the anorthosites used to give a very sort of certain age, a cluster of ages, and all these secondary lithologies that are thought to have intruded into the crust used to give another distinct age, a distinct younger age. And so you have these sort of two populations of ages, which is why people were starting to think, well, they must be two discrete episodes. But what a lot of the recent geochronology has reported is that actually there's a blurring of ages, and there's no clear transition, certainly in the geochronology, between the anorthosites and some of these secondary lithologies, which is why people have started to sort of come up with these other models of explaining quite what's going on. So yeah, there's a lot of blur, a lot of overlap, and it probably happened fairly rapidly.
We could probably stress that the importance of looking at the moon is that it is now relatively geologically inactive. There isn't any old stuff on the Earth, but that's because it's continually being reprocessed. These are presumably the earliest reprocessing events of your primary crust, essentially.
In terms of magmatic stuff, yeah, for sure. I mean, the surface of the moon obviously is always constantly being reworked by impacts and stuff. But all these samples were brought to the surface through an impact one way or another, and they all show various degrees of shock. And so the fundamental question that hadn't really been answered was, firstly, how shocked are they, and has that shock changed the relative proportions of trace elements within these crystals? Because they can move about a bit, I mean, through diffusion and all that kind of stuff. And well, luckily it turned out that they're not that shocked, and the trace elements don't appear to have been that heavily modified. So that's why you can then make these inferences about broader magmatic processes. But yeah, certainly in terms of the highlands, not much has really chemically or magmatically happened to these samples in 4 billion years. And that's just why there's such an important sample set for understanding these early parts of planetary building and building of rocky bodies, I guess.
Well, that sounds great, John. And where can people find that paper then?
People can find that in GCA, Geochemica or Cosmochemica Attica, which is in the same special issue as the paper that Roma was talking about.
Oh, yes.
Actor.
Just call it GCN.
When will it be out?
It's already out.
Oh,
so
grand,
yeah,
great.
we'll bung that link in the description.
Yeah. So if you guys
As of recording, it's the proofs haven't been typeset yet, but probably by the time this goes out, I imagine they probably will be.
And for everyone listening, just to inform you, next week I believe we're going to be doing a Q&A session. So if you guys tweet us questions.
Yep.
Or Facebook us questions. Preferably what we'll do is we'll put up a post saying we're going to be doing Q&A session and just comment on that post rather than sending us any digital messages over Facebook. And we'll try and answer a few of the most interesting ones we see.
Or the least interesting ones.
Or the least interesting, or just funny ones that we see. And we'll give you a shout out, of course, unless you don't want us to. So just let us know if you don't want us to say your name. But yeah, that'd be great. And thanks again, John, for telling us about your paper.
That's quite all right, Ricky.
Yeah, all right. Well, we'll
Brilliant.
see you all next week then.
Indeed.
Yeah. Bye-bye.
Bye.